Hi, so we're going to be starting with time-independent, non-degenerate perturbation theory. We did a quick recap in the previous video, but now we're going to get into a lot more detail. So, what is the problem that we want to solve? Well, we have some system described by some Hamiltonian H, and we do not know how to solve the time-independent Schrödinger equation, given by this expression right here. It's just an eigenvalue problem. It's the energy of our Hamiltonian, and this is the eigenstate of that energy. So we don't know how to solve it, but we're going to assume, or we're going to be dealing with the cases in which we can rewrite it as h naught plus some lambda hp, or rather as some w, okay? This h naught is what we call the unperturbed Hamiltonian, and it is a Hamiltonian that we do know how to solve. So we know the solution to this eigenvalue problem, and just really quickly, this is the energy levels, okay, and just denotes the different energy levels, and the 0 just denotes that it corresponds to this unperturbed Hamiltonian. Now these are the eigenstates for that energy. Again, the n just denotes the energy level, and the 0 denotes that we're dealing with the h naught Hamiltonian. So we are in the non-degenerate case. This just means that for each different energy level En, or rather En0, we have a different eigenstate phi n0. Now we know from quantum mechanics theory, we will do more videos on quantum mechanics theory in other playlists and other series of videos, but for now, just take it for granted that when we have the spectrum of a non-degenerate Hamiltonian, that is, all the eigenstates for different eigenvalues, they constitute a basis in our Hilbert space. And actually, if we choose these eigenstates to be normalized, they are an orthonormal basis. What does this mean? Orthonormal just means that when we take the inner product, denoted by this this bracket, okay, bracket notation, of two different elements of our basis, or two different eigenstates, we get the Kronecker delta. Just means that it is 1 for the same eigenstate, and it is 0 for the other ones. That is, they are orthogonal to each other, and because we only get 1 when we take the inner product, they are normalized. So they are orthonormal. Now, if they constitute a basis of H, then for all the elements of our Hilbert space, this calligraphic H, we can express it as a linear combination of the eigenstates of our original Hamiltonian, H naught, where the coefficients are just Cm. Now, what else? We are also going to assume that this W, which is what we call the perturbation, is really small compared to H naught. That is, we have originally some system which we do know how to solve, and we introduce some perturbation which is small. It's small, but it does change the energy levels. Then we can use perturbation theory. So we're going to assume it has this form. Now, we are going to write it as, we're going to manipulate our W in some way that we can write it like some parameter lambda, which we have just introduced it by hand, times the rest of Hamiltonian, which is HP. HP just means the perturbed Hamiltonian, or the perturbation. And this lambda is just gonna belong to the range 0 and 1. And we will see later, really, we are not gonna be doing anything because this lambda, we're just gonna be setting it equal to 1. But for now, just to keep track, as we will see later, of the orders, we're going to introduce this lambda, okay? But really, this lambda is nothing, it's just 1. So it doesn't really matter if we put it or not. And even if we weren't 1, you just substitute W like this and re-express the perturbation in terms of this new Hamiltonian, perturbation Hamiltonian. So we can rewrite this as this. Now, this is what we know and what we have assumed. What else? We are going to assume that we can express psi and E in terms of a power series in lambda. Okay, this is an assumption. Of course, they only hold if psi n, this n just stands for the yellow, we'll explain it afterwards, and the perturbation are analytic for lambda in this range. For more details, I put the books where I got this condition. You can check them out there in more detail. Oh well, the main point here is that we're going to be expressing it as a power series. We're going to be looking for solutions of this kind, and then the energy we're going to be assuming that it also has a power series expansion. If we expand it, we get that psi is just, okay, this zeroth term, careful, it's not psi raised to the zeroth power, it's just notation. The zeroth term, the term corresponding to lambda raised to the zeroth power, the term corresponding to lambda to the first power, and so on. E, zeroth order correction, first order correction because lambda is to the first power, and so on. So this is what I meant by keeping track of the order. When we expand the energy and the eigenstates, we are going to distinguish the different terms by the coefficients of lambda, of the different powers of lambda. So once we have all of this, we can get on with actually solving our problem. But before we do that, just again think about what we're doing. We have some system, original system H0, which we know that its energy levels are that. We're certain about this. Now we introduce some perturbation. Then our full Hamiltonian is of course the same energy level plus something else, which we don't know what it is. And this something else is due to this perturbation. Now, for a different energy level of H0, we will get a different energy level for H. So why don't we call this would be the full energy? So why don't we call this N? So this N just denotes that we are taking the nth energy level of H0 and calculating its correction. This will be a full term. So this is what this N stands for. And this N just means that it is the eigenstate of that full energy. So whenever I don't write any superscript, it is the full energy or the full eigenstate. And whenever I write a superscript, it just means that it is a correction. But this superscript just means that it corresponds to H0. If this is a bit confusing, you'll see later on how it's actually not that hard. So we have to get on with actually solving the time-dependent, independent Schrödinger equation. So what we have is this. We have H times psi n for some energy n, total energy, and this. Remember, we don't know how to solve this, so we are going to plug in our assumptions, and our full Hamiltonian actually just becomes, and actually, I'm going to just write it here, our full Hamiltonian just becomes H0 plus lambda HP. Okay, this is our Hamiltonian, but we can expand our ket, our eigenstate, in a power series expansion. So we're just going to go on and do it. We get this lambda k, this psi kth correction for n, for the nth energy, okay? Remember, all the subscripts and subscripts, don't get confused. Subscript n just means nth energy, superscript means the correction. And this is just the nth energy, but hey, wait a minute. This is a power expansion domain, so let's just plug it in. Goes from 0 to positive infinity of lambda k, the kth correction, and we are multiplying all of this times another time our series. So let's just plug it in once again. Now, let me just write it, and we'll get on with the next part. Notice that I have written here the Cauchy product. What is the Cauchy product? Well, we have two infinite power series, okay, which both start at 0 and go up to infinity. If these series converge, which we assume that they converge, okay, we're assuming that they converge to this psi and this en, and if one of them is absolutely convergent, we are assuming also now one of these two is absolutely convergent. Okay, if you don't want to assume that, just you could not do the process that we're going to be doing here. You have to multiply by hand, but you could try some problems. So we're going to make these two assumptions. So if all of this holds, then this product just becomes a single series in which the coefficients are just given by this other sum. So how does this translate in our case? Well, in our case, what we get is the following. And before we do that product, let me just split this into the term with h naught and the term with lambda h. So I'm going to write the sum k equals to 0 of h naught multiplying by all of this, h naught lambda k plus all of this, we're going to be putting it here. K goes from 0 to positive infinity of, well, hp and psi k. And instead of lambda k, we're going to have lambda k times lambda. So we can really just write lambda k plus 1. And all of this, okay, this is just the first part, is going to be equal to this product. And notice that I have been using the same index. If you want, I can use here this j. So if you're more comfortable with that, but this is really just a dummy index. And well, here I've written in terms of I and j. So let me just write this one as I. This is not a complex unity. This is just a dummy index. So we have this times this. Our x, in this case, would be lambda, and our terms would be, yes, en and psi j. So what we get, using the Cauchy formula, or Cauchy product, is the k goes from 0 to positive infinity of the sum going from L equals to 0 to k of AL. Okay, let's say that this is AL, or rather AI, and this would be BJ. So it would be AL, okay, it's just the same by replacing I with L, times this one, but instead of BJ, we have BK minus L. So whenever we get a J, we're going to write a K minus L. So instead of psi j, we're going to write psi k minus L. And this subscript n right here. And of course, right here we get our lambda k. Let me just erase this top part. Yeah, and actually I'm going to erase this too because we're going to be needing a lot of space. So, after expanding all of this, we get three sums. And I want you to notice just one thing. If I expand the zeroth term here, I can actually put these two sums together. You see what I mean? If I plug k equals 0 here, what do I get? Well, I get lambda to the 0, which is 1, okay? We get h naught times psi to the 0, okay? This is the 0th order correction, plus the sum going from k equals to 1, because we have already taken out the 0, positive infinity of, well, once again, h naught psi k n and lambda k. Sorry. And actually, to get more space, I'm going to write this here. So let me just erase this. Okay, so this would be our first term. But notice that if we do a change of variables here, we can get the sum going from 1 to positive infinity. That is, if instead of k, I use k plus 1, then our u is going to go from 0, if k is 0, it's going to go to 1, okay, if k equals 0, and if k goes to positive infinity, our u is going to go to positive infinity. So instead of using k, I'm going to write u, and u goes from 1 to positive infinity. I had a k here, so I have an u minus 1, and I have a k plus 1, so I have a u. But really, this is just a dummy index. So why not just write k instead again? A trick that I do usually is just to subtract 1 on the boundaries and to add 1 inside. But this is just the same as doing these change variables. So if we put this here, we get the following sum. We get the sum going from 1 to positive infinity of the perturbation times our k minus 1 correction, the nth energy, times lambda k. And this is equal to this sum right here. And no, I'm not going to write it right now, just remember that this is equal to s. And this is s, okay? This is equal to all of this. Now, we can put these two sums together into one sum, going from k equals 1 to positive infinity. So that's what I'm going to be doing here. So let me just erase this and actually write plus. Now, we can factor out this lambda k, and what we would get is that h naught phi n0 plus the sum is equal to this. So I'm just writing this right here. Factoring out this lambda k, we get h naught lambda k n plus hp psi k minus 1. Okay, so this would be our first part. This goes right here, and this one goes right here. So let me just erase this again. I hope that I'm not making you too confused with this erasing, but I'm sorry. So far we get that all of this is equal to this. Okay, what can we do now? Well, we could kind of put together this sum and this sum, but we're going from k equals 0 to positive infinity. So again, let's just subtract the k equals 1 term. If k equals 1, okay, then we get this sum going from L equals 0 to k to 1. So this would just be, well, of course, this lambda. Oh, no, sorry. K equals 0. Of course, let's just take out the k equals 0 term. So if this goes from 0, then we get L goes from 0 to 0. But this just means that we're substituting L by 0. So we just get these terms, and lambda to the 0th power is just 1. So we get this sum went from 0 to 0, but that's just one term. So we get En to the 0th power times this. K minus L. And again, I said L is only going from 0 to 0, so it's 0, and K is just 0, so we get the 0th order correction. Now, we are going to consider, well, as I said, we're going to consider one thing, that this first correction to the energy is our original energy. So instead of just writing these parentheses, we're going to write En0. Okay, so for 0, the 0th correction is actually just this energy. Okay, this is what we are assuming. So if we group terms, we can see, hey, wait a minute. This and this, we saw before that this eigenvalue equation holds. And now we have h naught times some eigenvalue, so some eigenvector, and this. So what can we say? Well, to 0th order, there's only one term that we have to think about. That is, let me just put it in a clearer way. This should be going from 1 now. What we're going to be doing now for all orders is grouping the terms with the same order. That is, if we have some term here multiplied by lambda, other terms, and some term here multiplied by lambda, then these two terms must be equal. We're going to assume that this holds, okay? But because this equation has to hold for all lambda. Now that we have taken out the k equals 0 term in all of this, what have we got? We got that in these two sums, there's not going to be lambda to the 0th power. The only two terms with lambda to the 0th power are this one and this one. So by this assumption, the way it's saying, these two terms have to be equal. So what we get here is what we call the 0th order correction. H naught, the correction to the 0th order to n power, is just En to the 0. But wait a minute. What is this phi or psi 0? Well, we get our H naught, applying it to some state, and it gives us E0 naught. But we said that there's only one possible state which satisfies this, that is phi and 0. So the first order correction to the energy, as we said, is this, and the first order correction to the wave function is our original wave function. So what we get in order 0 is that the 0th order correction is n0. This is by assumption, and that the 0th order correction to the wave state is just the eigenstate of H naught. So this is our first correction, our 0th order correction. Now, just remember that these 2 points are okay. This is just inequality. If we go to higher orders for k higher than 1, or equal to 1, or higher than 1, we get that this expression has to be equal to this one, right? Because we got, in general, this kth power and this kth power. So for all these general states, we get that this has to be equal to this. So let me just erase this, and I'll put it in a clearer way.